There is an object behind the sun right now. We call it 3-Eye Atlas, and today it reaches Perihelion, the closest point in its journey to our star. For most comets, perihelion is simply another milestone along an ancient orbit, a moment of peak brightness, maximum activity, and then the long fade back into darkness. But 3-Eye Atlas is not most comets, as it disappears behind the sun hidden from Earth's view in what astronomers are calling a perfect solar eclipse. From our perspective, a small but growing group of researchers has raised an uncomfortable question. What if this visitor from another star system didn't arrive here by accident? What if its trajectory, its timing, its very presence in our solar system at this precise moment in human history is not coincidence, but design? Harvard astrophysicist Avi Loeb has been asking a question since the object's discovery in July, a question that has sparked heated debate in scientific circles and captured public imagination worldwide. Is there any possibility, any chance at all, that 3-Eye Atlas is not entirely natural? Tonight, we're going to explore that question, not because we believe it's true, the overwhelming evidence suggests otherwise, but because in science, the most important questions are often the ones that seem impossible to ask. Questions that force us to examine our assumptions, refine our methods, and prepare for discoveries we cannot yet imagine. Right now, 203 million kilometers away, something is happening, something we cannot see. And in 8 days, when 3-Eye Atlas emerges from behind our star, we'll begin to learn what changed during those invisible hours. This is the story of an ancient traveler, a cosmic mystery, and the moment when humanity held its breath and wondered, are we alone? The asteroid terrestrial impact. Last Alert System wasn't designed to find interstellar objects. It was built to save lives. 4 telescopes, 4 locations spread across the globe: Hawaii, Chile, South Africa, each one scanning the night sky every single night looking for anything that moves against the static background of stars. The mission is elegantly simple: detect asteroids that might pose a threat to Earth and detect them early enough to do something about it. Atlas has been extraordinarily successful. Since its inception, the network has discovered thousands of near-Earth objects. Most are small, most are harmless, but a precious, terrifying few, would have been catastrophic if they'd gone undetected. The dinosaurs didn't have an early warning system. We do, and it works by taking repeated images of the same patch of sky and comparing them frame by frame. Anything that changes position between images gets flagged. Software algorithms analyze the movement, calculate trajectories, determine whether an object warrants further investigation. It's a process that happens thousands of times each night, mostly identifying known asteroids, occasionally finding new ones, and very rarely, extraordinarily rarely, discovering something that doesn't fit any category we have. On the night of July 1, 2025, the Atlas telescope in Rio Hurtado, Chile, was doing exactly what it was designed to do: scanning, comparing, cataloging the cosmic traffic of our solar neighborhood. And then, buried in the data stream, it found something unusual. The object was moving. That was normal. Everything in space is moving, pulled by gravity, following orbital paths, carved out billions of years ago. But this object was moving fast, much faster than typical asteroids, much faster than anything gravitationally bound to our sun's influence. The initial classification was routine new asteroid, moving object, track and catalog. But when astronomers looked closer at the velocity data, something immediately stood out. This wasn't just fast. This was escape velocity fast. Let's establish some context here, because the speeds involved are difficult to comprehend from our perspective here on Earth's surface. Our planet orbits the Sun at approximately 30 kilometers per second. That's about 108,000 kilometers per hour, or roughly 67,000 miles per hour. We're hurtling through space at speeds that would make a bullet seem to stand still. But we don't feel it because everything around us, the atmosphere, the moon, our fellow travelers on this planetary ship, is moving at the same speed. Mercury, being much closer to the Sun, has to orbit even faster to avoid falling into our star's gravitational well. It travels at about 48 kilometers per second, carving its tight orbit in the intense heat and radiation near the Sun. The object detected by Atlas was clocked at 58 kilometers per second. And it was doing this out near Jupiter's orbit, where gravitational speeds should be much, much slower.
Where objects should be lumbering along at a fraction of that velocity. That's when astronomers knew they were looking at something special, something that didn't belong. When you trace the orbit of an object backward through time, running the gravitational equations in reverse, you can determine where it came from. For most objects in our solar system, this calculation leads back to the Sun. They've been orbiting our star for billions of years, following elliptical paths that bring them closer and farther away, but never truly escaping. Gravitationally bound, solar system citizens. But when astronomers traced 3I Atlas backward, the numbers told a different story. The orbit was hyperbolic, not elliptical. Hyperbolic orbits are open. They don't loop back. They're one-way tickets through the solar system, marking objects that came from somewhere else and are heading somewhere else, briefly passing through our cosmic neighborhood like travelers at a rest stop. The designation was made official on July 2, 2025. The E3I prefix was added to its name. Third interstellar object. The third confirmed visitor from beyond our solar system to pass through our neighborhood. A messenger in a bottle thrown across an ocean of stars. Before we go further, we need to talk about those other two visitors, because the story of 3I Atlas only makes sense in the context of what came before. The story of how we learned that we are not alone in the galaxy, at least not in the sense that objects from other star systems occasionally pass through ours. The question is, are these objects entirely natural? Or might some of them be something more? October 19, 2017. A telescope in Hawaii spotted something odd moving through the inner solar system. It was small, moving fast, and its trajectory was all wrong for anything that belonged here. When astronomers calculated its orbit and traced it backward, they found something unprecedented in human history. This object had come from outside our solar system. It was the first confirmed interstellar visitor we had ever detected. They named it Oumuamua, the Hawaiian word for scout or messenger. The name was prophetic in ways we didn't yet understand. Oumuamua was strange from the very beginning. Its shape was unusual, long and thin, like a cigar or perhaps a pancake, depending on which analysis you believed. It tumbled through space in an odd rotation pattern. And most puzzling of all, it accelerated as it left the inner solar system, pushed by some force that astronomers couldn't immediately explain. Dr. Avi Loeb of Harvard University suggested that Oumuamua might be artificial, a solar sail perhaps, or some kind of technological artifact. The idea was controversial, to put it mildly. Most scientists argued that the acceleration could be explained by outgassing the release of trapped gases as the object warmed near the sun, acting like tiny rocket thrusters pushing it along. But the debate sparked something important. It made scientists realize that interstellar objects could look very different from what we're used to seeing in our own solar system, that our expectations built on billions of years of observing our own cosmic backyard might not apply to visitors from elsewhere. 2 years later, in August 2019, amateur astronomer Gennady Borisov discovered the second interstellar visitor. Using a telescope he built himself in his backyard. Think about that for a moment. The second confirmed interstellar object in human history was discovered not by a billion-dollar space telescope, not by a professional observatory, but by an amateur astronomer in Crimea who simply loved looking at the sky. This one was different. 2I Borisov looked like a comet. It acted like a comet. It had a visible coma, a cloud of gas and dust surrounding its nucleus, and a tail streaming behind it, pushed by solar radiation pressure. Spectroscopic analysis showed water vapor, carbon monoxide, and other compounds you'd expect from a typical solar system comet. Borisov was in many ways reassuringly normal. It suggested that comets throughout the galaxy probably look similar to our own. Same basic composition, same basic physics. The universe, it seemed, follows the same rules everywhere. And then 6 years after Oumuamua and 6 years after Borisov came 3I Atlas. It's helpful to compare all three objects side by side because the differences tell us something profound about the diversity of the galaxy. Oumuamua was small, maybe 400 meters across at its longest point, probably a fragment of something larger tumbling through interstellar space for who knows how long. It showed no obvious cometary activity, no coma, no tail. Just a dark, reflective surface that rotated every 7.3 hours. 2I Borisov was larger, about 1 kilometer in diameter, very clearly a comet with a bright coma visible even from Earth-based telescopes. It moved at about 32 kilometers per second relative to the Sun, carrying the chemical signature of carbon monoxide, suggesting it formed in a cold, distant region of its home system. 3I Atlas is much larger. Initial estimates placed its diameter at 5.6 kilometers, though more recent analysis suggests it could be even bigger. Some calculations put its mass at approximately 33 billion tons, roughly the mass of Manhattan, but compressed into a ball of ancient ice and rock. Its speed, 58 kilometers per second, is nearly double that of the previous two visitors. But size and speed aren't the only differences. The trajectory is what makes some scientists pause, what makes them furrow their brows and double-check their calculations. Oumuamua came from the direction of Vega, approaching from above the plane of the solar system at a steep angle. It was like someone had thrown a rock over a fence coming in from the north, passing through at an angle leaving to the south. 2I Borisov approached at a less extreme but still significant angle, coming in from the direction of the constellation Cassiopeia, again well above the ecliptic plane, the flat disk where all the major planets orbit. 3I Atlas is different. It's coming in nearly perfectly aligned with the ecliptic plane. The angle of deviation is just 4.89 degrees off. For context, Pluto's orbit, which is considered quite tilted and eccentric, is 17 degrees off the ecliptic. 3I Atlas is hugging the plane of the planets more closely than many objects that actually belong to our solar system. This alignment is statistically unusual. Space, after all, is three-dimensional. An interstellar object can approach from literally any direction above, below, from the side, at any angle. The celestial sphere offers essentially infinite approach vectors. The probability of randomly arriving within 5 degrees of the ecliptic plane is less than 0.2%, 1 in 500. Some scientists argue this isn't necessarily suspicious. The Milky Way galaxy itself has a disk structure, and most stars orbit roughly within that galactic plane. Objects ejected from other star systems might naturally tend to follow paths roughly aligned with the galactic disk, which happens to be oriented similarly to our solar system's ecliptic, but it's still unusual. And combined with everything else we've observed about 3I Atlas, it adds to a growing list of peculiarities that make this object worth examining very, very carefully. There's another major difference worth noting: the direction of origin. Both Oumuamua and Borisov came from directions where the Sun was moving toward them as it orbits the galactic center. We sort of ran into them as they drifted through space like a car on a highway, encountering bugs on the windshield. 3I Atlas is coming from the side, a T-bone approach from the direction of the galactic core but perpendicular to our direction of motion through space. This trajectory brings it unusually close to several major planets in our system. On October 3, 2025, it passed within 29 million kilometers of Mars, close enough that spacecraft orbiting the red planet could photograph it. In March 2026, if current projections hold, It will pass within 54 million kilometers of Jupiter, where NASA's Juno probe might get a glimpse. The probability of an interstellar object randomly passing this close to multiple major planets on a single trajectory, less than 0.005%, 5 in 100,000. Now let's be very clear about what these probabilities mean and what they don't mean. Low probability doesn't mean impossible. If you flip a coin 10 times, the probability of getting exactly the sequence heads, tails, heads, heads, tails, tails, heads, tails, heads, tails is about 0.1%, but some sequence has to occur. Unlikely things happen all the time simply because so many things are happening. Millions of interstellar objects probably pass through our solar system over millions of years. Some will inevitably have unusual paths purely by chance. Statistical outliers are expected when you're drawing from a large population, but the numbers are worth noting. Because when you start adding up all the unusual characteristics of 3I Atlas, the alignment, the trajectory, the close planetary encounters, the size, the speed, you start to see why some scientists are paying very, very close attention. In a three-dimensional universe, why would a cosmic wanderer choose the flattest path through our system? Why would it arrive at just the right angle, just the right time to pass close to the most interesting targets, the rocky inner planets and the gas giant outer planets? Is it coincidence? Almost certainly yes. Is it worth investigating carefully? Absolutely. Because if this object were not entirely natural, this is exactly the trajectory it would take. But before we can discuss that hypothesis responsibly, we need to understand what this object is actually made of. We need to talk about the chemistry problem. The first detailed observations of 3I Atlas came from the Hubble Space Telescope on July 21, 2025. Orbiting high above Earth's atmosphere, free from the distortions and absorptions that plague ground-based observations, Hubble turned its powerful eye toward this interstellar visitor and captured something astronomers both expected and didn't expect to see. The images showed a bright, teardrop-shaped cocoon of dust surrounding the object's nucleus. This is normal for comets as they approach the sun. The solar radiation heats the surface, causing ice to sublimate, turning directly from solid to gas without passing through a liquid phase. This gas, along with dust particles carried along with it, creates the familiar glowing cloud we call a coma. What wasn't normal was how early this coma appeared. When Hubble captured those images, 3I Atlas was still 364 million kilometers from the Sun. That's about 2.4 astronomical units, well beyond Mars's orbit, out where the Sun appears smaller and colder in the sky. At that distance, most solar system comets are still frozen solid. The Sun's heat hasn't penetrated deep enough to cause significant sublimation. They're quiet, dormant, barely distinguishable from asteroids. But 3I Atlas was already active, already outgassing, already producing a visible coma that glowed in Hubble's images. This suggested the object was made of something more volatile than water ice, something that could sublimate at much lower temperatures much farther from the Sun's warmth. On August 6, 2025, NASA's James Webb Space Telescope, the most powerful infrared observatory ever built, pointed its near-infrared spectrograph at 3I Atlas. If Hubble showed us what the object looked like, Webb would tell us what it was made of. Spectroscopy is one of the most powerful tools in all of astronomy. It's how we can determine the composition of objects billions of light years away without ever touching them, without ever sending a probe. By analyzing the wavelengths of light coming from an object, we can identify the chemical fingerprints left by different elements and compounds. Each element and compound absorbs and emits light at specific wavelengths, creating a unique signature as distinctive as a barcode. Hydrogen has its pattern, oxygen has its pattern, carbon dioxide, methane, ammonia, each leaves its mark on the spectrum of light. The Webb data revealed something unexpected. The coma of 3I Atlas was dominated by carbon dioxide CO2 gas, not water vapor, not carbon monoxide.
carbon dioxide in a ratio of about 8:1 compared to water. This is essentially the opposite of what we see in typical solar system comets, where water ice is the primary component, and CO2 is a minor constituent, usually making up less than 10% of the volatile inventory. The implication was immediately clear to planetary scientists. 3I Atlas formed in an extremely cold environment, colder than the outer regions of our own solar system, in conditions where carbon dioxide ice was more abundant than water ice, or at least where CO2 was deposited in outer layers that are now sublimating away. This makes sense for an interstellar object. Out in the depths of space, far from any star's warmth, temperatures can drop to just a few degrees above absolute zero. Under those conditions, carbon dioxide would freeze readily, potentially dominating the composition of any comet that formed in the outer reaches of another star's planetary system. But the chemistry story gets stranger, and this is where things become genuinely puzzling. In September 2025, astronomers using the Keck 2 telescope with its powerful spectrograph detected something unusual in the light coming from 3I Atlas. Nickel vapor. Specifically, they detected emission lines consistent with nickel atoms in the object's coma being released at a rate of about 4 grams per second. This might not sound like much, but it's significant. Metals don't typically sublimate from comets unless they're very close to the sun and very hot. And even then, you see multiple metals together, the same mix of elements that formed in stellar cores, and were scattered into space by supernova. But the truly puzzling aspect was what they didn't detect. Iron. In every known comet, both from our solar system and from interstellar space, nickel and iron appear together. This makes perfect sense from a nucleosynthesis perspective. Both metals form in the cores of dying stars through similar processes. When a supernova explodes, scattering these elements throughout space, they get incorporated into new star systems as they form. The cosmic dust that builds planets and comets contains both nickel and iron, typically in roughly equal proportions. The nickel-to-iron ratio in comets is usually close to 1:1, sometimes varying by a factor of a few, but both metals are always present. Always. In 3I Atlas, the ratio appeared to be heavily skewed toward nickel. The amount of iron was below detection limits. It was as if someone had separated these chemically similar elements, extracting the nickel while leaving the iron behind. This sparked immediate discussion in the scientific community. What natural process could separate nickel from iron so completely? How could a comet form with this unusual metal composition? Some researchers suggested that the carbon dioxide in the coma might be reacting with nickel-bearing dust grains to form nickel carbonyl, a complex molecule where nickel atoms bond with carbon monoxide groups. This compound is volatile and could explain why nickel appears as a gas while iron remains locked in solid dust particles. The interesting thing about nickel carbonyl, and this is where the speculation really begins, so let's be clear about that, is that on Earth, it's primarily known as an industrial chemical. It's used in metal refining processes. The Mond process specifically uses nickel carbonyl to purify nickel metal, separating it from iron and other contaminants. Finding this compound in space isn't impossible. The conditions needed to form it, carbon monoxide nickel and moderate temperatures, can exist naturally in a cometary coma. But it's unusual, it's exotic, and it adds another data point to the growing list of 3I Atlas's peculiarities. This is speculation, but some have suggested if you were designing a spacecraft, you might use nickel alloys for their strength-to-weight ratio and resistance to corrosion. If that spacecraft were heated by the sun, and if those alloys reacted with carbon-based compounds on its surface, you might see nickel vapor without iron. But let's be very careful here. Unusual chemistry is not evidence of artificial origin. The universe is vast and varied. Conditions in other star systems can be radically different from our own. An interstellar comet that formed 7 to 10 billion years ago in a different stellar environment, with different initial chemical abundances exposed to different radiation fields, Such an object could easily have chemistry we've never encountered before. Then in late September, something changed. Astronomers detected iron in the coma for the first time. The nickel-to-iron ratio quickly shifted towards something more normal, more familiar. Whatever process had been suppressing iron emission apparently stopped, or conditions changed to allow both metals to sublimate together. This pattern of sudden changes would repeat several more times as 3I Atlas approached the Sun. Changes that suggested a complex internal structure with different layers exposed at different times. By late September, as the object passed through 1.5 astronomical units, about halfway between Earth and Mars, it began releasing massive amounts of water vapor. The emission rate was described by observers as equivalent to a fire hose running at full blast. Far more than astronomers would expect from a comet at that distance. The water release was so sudden and so intense that it caught observers by surprise. Most comets gradually increase their activity as they approach the Sun. The sublimation builds slowly, predictably, following curves that match the inverse square of distance to the Sun. 3I Atlas seemed to turn on like a switch. 1 week, minimal water. The next week, torrential outgassing. This behavior suggested several possibilities. Perhaps the carbon dioxide ice near the surface had sublimated away, exposing underlying layers of water ice. Perhaps cracks or fissures in the nucleus suddenly opened, allowing trapped water to escape from interior reservoirs. Or perhaps the internal structure of the object was fundamentally different from solar system comets, layered like an onion with different compositions at different depths. That last possibility is worth considering carefully. If 3I Atlas formed 7 to 10 billion years ago, as its trajectory suggests, it would have experienced countless cycles of cosmic radiation, temperature fluctuations, and possibly collisions during its journey through interstellar space. Its internal structure might be fractured, layered, or heterogeneous in ways that typical solar system comets, which have been safely stored in the Kuiper belt or Oort cloud for most of their existence, are not. These are messages written in ice, chemical signatures of conditions in another stellar system billions of years ago. Every spectrum we capture, every emission line we measure, is a glimpse into a world we will never visit, around a star we may never identify. The chemistry of 3I Atlas is telling us a story about its birthplace, its journey, and its nature. But chemistry isn't the only unusual feature of this object. There's something else. Something visible in photographs that has sparked even more debate. We need to talk about the tail that points the wrong way. Let's return to that September discovery because it deserves a deeper examination. The nickel without iron observation has become something of a flashpoint in the debate about 3I Atlas's nature. To some scientists, it's an interesting anomaly with exotic but natural explanations. To others, it's Exhibit A in the case for non-natural origin. Dr. Avi Loeb has been particularly vocal about the significance of this finding. In interviews and scientific papers, he has repeatedly emphasized that nickel carbonyl, the proposed explanation for the nickel vapor, is a compound that on Earth is almost exclusively associated with industrial processes. This was never observed for any other object, Loeb stated in one interview. This was a process that we can imagine only because it was used in industry. The Mond process, developed in the 1890s by Ludwig Mond, is elegant in its chemistry. When carbon monoxide gas is passed over impure nickel at about 50 degrees Celsius, it forms nickel carbonyl NiCO4. This gaseous compound can then be decomposed at higher temperatures to produce pure nickel metal. It's how we refine nickel on an industrial scale. It's how we create the high-strength nickel alloys used in everything from jet engines to spacecraft hulls. The question Loeb poses is straightforward. How does nature produce this compound at the quantities observed in 3I Atlas? The answer from the mainstream scientific community is, we're not entirely sure, but here are some possibilities. First, the conditions in a cometary coma are genuinely unusual. You have solid dust grains, some of which contain nickel from the original protoplanetary disk, being heated by sunlight and surrounded by a gas of carbon monoxide and carbon dioxide.
The grains are small, meaning they have a high surface area to volume ratio. The temperatures vary wildly depending on sunlight exposure. And crucially, the pressure is essentially zero-A vacuum that allows chemical reactions that would never occur in Earth's atmosphere. In this environment, carbon monoxide molecules could potentially bond with nickel atoms on the surface of dust grains, forming nickel carbonyl that then evaporates into the coma. It's exotic chemistry, yes, but not impossible chemistry. Second, the initial absence of iron might have been an observational artifact. Iron has different spectral lines than nickel. Some are easier to detect than others, depending on temperature density and excitation state. It's possible that iron was there all along, but in a form that wasn't emitting light at wavelengths we were observing. The fact that iron appeared later as the comet got closer to the sun and warmed up supports this interpretation.
Both metals were present, but under the cooler conditions farther from the sun, only nickel was sublimating or emitting detectable light. Third, and this is more speculative, the composition of the dust in 3I Atlas might genuinely be different from what we're used to seeing. If it formed in a stellar environment with unusual abundances, perhaps around an older, metal-poor star, or in a region enriched by a specific type of supernova, the nickel-to-iron ratio could be skewed from what we consider normal. These are natural explanations. They require somewhat special conditions, but nothing that violates known physics or chemistry. But Loeb's argument isn't that natural explanations are impossible. It's that we should consider all hypotheses when we encounter something we've never seen before. The artificial hypothesis, he argues, deserves serious investigation because the consequences of dismissing it without proper examination could be profound. If 3I Atlas were, and let's be very clear that this is highly speculative, if it were a manufactured object, perhaps a spacecraft or probe, what might we expect its composition to be? Nickel alloys are popular in aerospace engineering. In Conal, for example, a nickel-chromium-based superalloy is used in high-temperature applications like rocket engines and spacecraft structures. These alloys are chosen for their strength, temperature resistance, and durability in harsh environments. An interstellar probe traveling for billions of years through the radiation and micrometeorite impacts of deep space would need materials that could withstand extraordinary abuse. If such a probe were coated with carbon-based compounds, perhaps ablative shielding, perhaps organic materials accumulated during its journey, and if this coating reacted with the nickel alloy when heated by the sun, you might indeed see nickel vapor with relatively less iron. This is speculation. It's important to label it as such. There's no direct evidence supporting this interpretation over the natural explanations. But it's a hypothesis that makes predictions, and predictions can be tested. If 3I Atlas is natural, we would expect the nickel-iron ratio to normalize as it warms up and deeper layers are exposed. We would expect the metal emissions to follow patterns consistent with known cometary behavior tied to solar heating, varying with rotation, potentially showing correlation with dust production. If it's artificial, we might see different patterns. Perhaps sustained nickel emission even at distances where natural sublimation should have ceased. Perhaps variations in emission that don't correlate with solar distance or rotation. Perhaps other metals appearing in ratios that don't match cosmic abundances. As of late September 2025, all observations have been consistent with natural processes. The iron appeared. The ratios began to normalize. The emission patterns followed expected thermal curves, but the nickel without iron observation has entered scientific history as one of the most unusual findings in cometary science. Whether it represents exotic but natural chemistry or something more, remains one of the genuine mysteries of 3I Atlas. A mystery that, as we'll see, is just one piece of a larger puzzle that has some scientists genuinely concerned, and others rolling their eyes in frustration at what they see as speculation run amok. The debate over this single chemical signature reflects a deeper tension in astronomy. When do we stick with conventional explanations, and when do we seriously entertain unconventional ones? It's a question that has no easy answer. What we know for certain is this: 3I Atlas contains nickel. It released that nickel in unusual patterns. And for a brief window, in September 2025, that nickel was visible without its usual companion iron, creating a chemical puzzle that scientists are still working to fully explain. Comets are defined by their tails. It's how we recognize them, how we've known about them for thousands of years. A bright head, a long streaming tail moving slowly across the night sky over weeks or months. Ancient civilizations saw them as omens. We now understand them as icy relics from the formation of the solar system temporarily illuminated during their passage close to the sun. The tail of a comet is created by solar wind and radiation pressure. As the comet approaches the sun, ice on its surface sublimates into gas. This gas, along with dust particles, lifted off the surface, streams away from the nucleus in all directions. But the solar wind, a constant stream of charged particles flowing outward from the sun at hundreds of kilometers per second, pushes this material preferentially in one direction, away from the sun. This is fundamental cometary physics. It's been observed and confirmed countless times. A comet approaching the sun has its tail streaming behind it, like hair blown back by wind. A comet leaving the sun has its tail streaming in front of it, like a person walking backward into the wind. But in both cases, and this is the key point, the tail points away from the star, always away, never toward. So when astronomers using the Keck 2 telescope in Hawaii captured images of 3I Atlas in August 2025, they were genuinely surprised to see something unusual: a jet of material pointing toward the sun. Not a tail, a jet, a narrow, focused stream of gas and dust extending about 10,000 kilometers from the nucleus, aimed directly at the sun, against the solar wind, against radiation pressure, against everything we know about how cometary material should behave. This feature, sometimes called an anti-tail, is not completely unheard of in comets, but it's rare, and the mechanism behind it is often misunderstood. True anti-tails typically form when a comet's orbital geometry creates an optical illusion. From certain viewing angles, parts of the comet's normal dust tail can appear to extend forward. It's a perspective effect, like how railroad tracks seem to converge in the distance even though they're actually parallel. But the jet observed on 3I Atlas wasn't an illusion. The spectroscopic data confirmed it. Material was actually moving toward the sun, not optically appearing to move that way, actually moving that way against the forces that should be pushing it back. There are natural explanations for this. One involves the rotation of the comet's nucleus. Imagine the nucleus as a rough, irregular potato-shaped object spinning through space. As it rotates, different parts of its surface face the sun at different times. If a particular active region, a patch of volatile ice, happens to be oriented toward the sun at just the right moment in the rotation cycle, it can create a jet that sprays toward the sun. Think of it like a lawn sprinkler. As the sprinkler rotates, water shoots out in different directions. From any one viewing angle, you might see water moving toward you or away from you, depending on where the sprinkler is pointed at that moment. As the cometary nucleus rotates, this jet would sweep through space like a lighthouse beam. We might see it pointing toward the sun for a few hours or days. Then, as the active region rotates out of view, the jet disappears or changes direction. This explanation is physically plausible. It requires nothing beyond normal cometary behavior. Multiple solar system comets have shown exactly this kind of activity. Another explanation involves the size and velocity of dust particles. If the dust grains being ejected from the active region are unusually large and heavy, Perhaps several millimeters or even centimeters across, they might not respond immediately to solar radiation pressure. They'd continue moving in their initial direction, the direction they were thrown by the sublimating gas for quite a while before eventually being pushed back into the normal anti-solar direction. This could create a temporary forward-pointing structure. Think of throwing sand into the wind. The individual grains initially move in the direction you throw them, but the wind gradually changes their trajectory. If you could freeze time at just the right moment, you'd see a spray of sand moving against the wind direction at least temporarily. Both explanations are physically plausible. Neither requires anything beyond natural processes. But the timing was interesting. The sunward jet was observed primarily in July and August 2025, when 3I Atlas was still relatively far from the sun, about 2 astronomical units out. By September, when other telescopes captured new images, the jet had transformed into a more conventional tail pointing away from the sun. This transition is exactly what you'd expect if the jet was being caused by volatile ices sublimating on the sunward side of the nucleus. Early on, when the comet is still relatively far from the sun, the solar wind isn't strong enough to immediately overpower the initial velocity of the ejected material. The gas and dust shoot out toward the sun, at least initially. But as the comet gets closer and the solar wind intensifies, the physics change. The radiation pressure and particle bombardment become strong enough to immediately push material back. The directional jet becomes an anti-solar tail. Standard cometary behavior reasserts itself. This is the mainstream interpretation. But there's another perspective worth examining, even if it's speculative, even if most scientists consider it unlikely. Dr. Avi Loeb and colleagues published a paper in October exploring what he calls a pedagogical exercise, a thought experiment about what an artificial interstellar object might look like. In this framework, the sunward jet takes on a different interpretation. If you were piloting a spacecraft approaching a star at high speed, and if you wanted to slow down, you would fire your engines. Specifically, you'd fire a braking thruster. And that thrust would point toward the star, toward the direction you want to slow down from. The exhaust from such a thruster would appear as a jet pointing toward the sun. In this interpretation, the jet visible in July and August wasn't sublimating ice at all. It was propulsion, a braking burn to reduce the object's velocity before its closest approach to the sun. And when the jet disappeared in September, that wasn't the solar wind overpowering it. That was the engines shutting off. The maneuver was complete. This is, to be absolutely clear, speculation. Creative speculation that makes for fascinating thought experiments, but isn't supported by the bulk of the evidence. Here's why the mainstream is skeptical. If 3I Atlas were under power during July and August, we would expect to see changes in its trajectory. The object would be accelerating, or in this case decelerating, in a way that couldn't be explained by gravity alone. Orbital calculations would show residuals deviations from the predicted path. No such deviations have been detected. Thousands of position measurements from May through September 2025 show residuals consistent with gravitational motion only. The orbit follows exactly the path we'd expect from an object moving under the influence of the sun's gravity alone, with perhaps tiny perturbations from asymmetric outgassing, but nothing that would indicate a major propulsive event. There's also the question of efficiency. If you're traveling through interstellar space for billions of years, you need to be extremely efficient with your propulsion. Every gram of propellant is precious. Would you really execute a months-long low-thrust braking maneuver when you could wait until perihelion and do a much more efficient high-thrust burn using the Oberth effect? The answer from any competent mission planner would be no. You'd wait. You'd coast until the optimal moment. Which brings us to where we are today. October 29th, 2025, Perihelion. The moment when, if any propulsive maneuver were planned, it would happen. And we can't see it. Remember this observation, it returns in an unexpected way. To understand why 3i Atlas has captured such intense scientific attention, we need to understand just how rare and extraordinary these interstellar visitors are. We need to appreciate that until 2017, we had never confirmed even a single object from outside our solar system passing through our neighborhood. Think about that. For all of human history, for all the centuries of astronomical observation, for all the decades of sophisticated telescopes and computer modeling, we had never detected an interstellar visitor. We theorized they should exist. Basic calculations suggested that planetary systems must occasionally eject objects through gravitational interactions, and those objects must wander the galaxy. But we'd never actually seen one. Oumuamua changed that. On October 19, 2017, astronomer Robert Warwick was reviewing images from the Pan-STARRS telescope in Hawaii when he noticed an object moving unusually fast. Within days, astronomers worldwide were tracking it, calculating its orbit, and realizing they were witnessing history. The object was already leaving. By the time we detected it, Oumuamua had already passed Perihelion and was heading back out into interstellar space. We only caught it on the way out, like noticing a guest at a party just as they're walking out the door. Initial observations showed an object about 400 meters long, dark red, in color, tumbling end over end with a rotation period of about 7.3 hours. But the most puzzling feature was its acceleration as it left the inner solar system. As astronomers tracked its position over subsequent weeks, they noticed it was moving slightly faster than it should be based on gravity alone. Something was pushing it. The natural explanation was outgassing. Even though no coma or tail was visible, the object could still be releasing small amounts of gas as it warmed near the sun. This gas escaping from specific regions on the surface would act like tiny rocket thrusters, giving the object a small but measurable push. This explanation works. It's been observed in solar system comets, but there was something odd. We couldn't detect the gas that would cause such acceleration. No water vapor, no carbon monoxide, nothing in the spectroscopic observations that would explain the magnitude of the push. Dr. Loeb suggested an alternative. What if Oumuamua was a light sail? A thin, reflective sheet pushed by solar radiation pressure. Such a sail, if artificial, could explain both the unusual shape, very flat, and the acceleration radiation pressure is stronger than outgassing for thin objects. The idea sparked fierce debate. Most astronomers argued that natural explanations, while requiring some special pleading, were still far more likely than invoking alien technology. The principle of parsimony, preferring simpler explanations over complex ones, suggested we should exhaust natural possibilities before considering artificial ones. Oumuamua left the solar system before we could gather enough data to resolve the debate definitively. It's now beyond the reach of even our most powerful telescopes, forever carrying its mysteries with it into the void. 2 years later came 2I Borisov, and it was almost a relief to astronomers. This object behaved exactly as expected. It had a clear coma and tail. Spectroscopy showed water vapor and carbon monoxide in expected ratios. Its activity level correlated perfectly with its distance from the sun. If you had to design a stereotypical comet to ease nervous astronomers worried about alien probes, you'd design Borisov. It was beautiful. Professional and amateur astronomers worldwide observed it for months as it passed through the inner solar system. Some of the images captured by Hubble and ground-based telescopes looked like textbook examples of what a comet should look like. Borisov taught us that interstellar comets can be reassuringly normal, that despite forming around another star in another protoplanetary disk billions of years ago, they can still follow the same basic physics and chemistry that governs our own comets. But it also taught us that Oumuamua was genuinely weird. Even compared to another interstellar visitor, Oumuamua stood out as unusual. Dry, dark tumbling, accelerating. Whatever it wasn't typical. And now we have 3i Atlas, The third data point, and it's different again. 3 visitors, 3 completely different profiles. Oumuamua, small, enigmatic, possibly a fragment showing unexplained acceleration. Borisov, medium-sized, cometary textbook, normal in behavior. 3I Atlas large, fast, chemically unusual with a trajectory that has some scientists raising eyebrows.
This diversity tells us something profound about the galaxy. There isn't one type of interstellar object. There isn't even a spectrum from typical to unusual. There's enormous variety. Different star systems produce different kinds of planets, asteroids, and comets. Different formation conditions lead to different compositions. Different ejection mechanisms lead to different trajectories and rotation states. We're sampling the galaxy one visitor at a time. Each one is a postcard from a different cosmic neighborhood, showing us conditions we might never have imagined. Oumuamua might have been a fragment from a planet that was torn apart during formation, or a comet so old and so cooked by cosmic rays that all its volatiles had evaporated, leaving just a rocky core, or something else entirely.
Borisov formed in a cold carbon monoxide-rich environment, possibly around an M-dwarf star, where the frost line, the distance at which water ice can condense, is much closer to the star than in our own system. 3I Atlas formed somewhere that favored carbon dioxide over water. Somewhere old, possibly very old, during an era when the galaxy had different chemical abundances. It's been wandering for an extraordinarily long time, accumulating cosmic ray damage, surviving impacts, slowly changing in ways we can only infer. These are time capsules. Each one carries within its chemistry and structure the history of another place, another time. By studying them, we're conducting reconnaissance of the galaxy without ever leaving our own solar system, and if the Vera C. Rubin Observatory delivers on its promise, we'll soon be discovering one or more of these visitors every month. Within a decade, we might have a catalog of hundreds, each one unique, each one teaching us something new about the conditions, processes, and variety of planetary systems throughout the Milky Way. But right now, in this moment, we have 3. And the third one is happening right now, reaching its closest point to the sun, undergoing the most intense transformation of its billion-year journey. And we can't see it. October 3rd, 2025. While most of Earth's telescopes were tracking 3I Atlas from a distance of over 300 million kilometers, another set of eyes, robot eyes, artificial eyes we had built and sent to another world, had a much closer view. 3I Atlas passed within 29 million kilometers of Mars that day. In cosmic terms, that's practically grazing distance. Close enough that spacecraft orbiting the red planet could turn their cameras toward this interstellar visitor and capture images with detail impossible to achieve from Earth. Multiple missions had been tracking the comet for weeks, calculating when the closest approach would occur, planning observation sequences. The European Space Agency's Mars Express and ExoMars Trace Gas Orbiter were both positioned to observe. NASA's Mars Reconnaissance Orbiter, with its powerful high-rise camera, had the object in its sights. Even the Perseverance rover on Mars's surface pointed its cameras skyward, hoping to catch a glimpse. The challenge was immense. These spacecraft and rovers were designed to photograph Mars, a bright, sunlit world, just hundreds or thousands of kilometers away. 3I Atlas was 29 million kilometers away and roughly 10,000 to 100,000 times fainter than the Martian surface. It was like trying to photograph a candle flame from across an entire city, but they managed it. On October 7, 2025, the European Space Agency released the first images from the ExoMars Trace Gas Orbiter. The world held its breath, wondering what we would see. The images showed exactly what mainstream scientists predicted: a fuzzy white dot. A faint, slightly extended blob of light drifting steadily downward against a backdrop of black space and pinpoint stars. There was no mothership, no geometric structures, no lights, no evidence of artificial construction. It looked quite simply like a small comet 29 million kilometers away. The animated sequence from the TGO orbiter is actually quite beautiful in its simplicity. Frame after frame shows 3I Atlas moving against the stellar background, its coma clearly visible as a diffuse glow around the nucleus. The motion is steady, predictable, exactly what you'd expect from an object following a gravitational trajectory. The images captured the halo of gas and dust surrounding the nucleus, the coma that forms when volatile ices sublimate in sunlight. Analysis of the coma's size and brightness provided clues about the outgassing rate and the size of the nucleus itself. Mars Express provided similar images, slightly different angles, slightly different resolutions, but all showing the same thing, a comet. An active outgassing, completely normal-looking comet, at least at the resolution available from 29 million kilometers. We even got a view from the surface. NASA's Perseverance rover sitting in Jezero crater, the dried-up lakebed where it's been searching for signs of ancient microbial life, turned its Mastcam Z camera toward the night sky above. The resulting images were challenging. The comet was incredibly faint, right at the edge of what the camera could detect against the glow of the Martian atmosphere and the scattered starlight. You couldn't see much in the raw images, but astrophotographer Simeon Schmauhaus had an idea. He downloaded the raw image files that NASA makes publicly available, stacked multiple exposures on top of each other to reduce noise, and carefully processed them to enhance faint signals. And there, right where the comet was predicted to be, he found it. A faint streak of light, a super faint smudge against the background. It was confirmation. The interstellar visitor was visible even from the surface of Mars, the first interstellar object ever photographed from the ground of another world. These observations were valuable for several reasons beyond their inherent coolness. First, they provided parallax measurements. By observing the same object from multiple locations, millions of kilometers apart, we could triangulate its position with extreme precision, helping refine our models of its trajectory and timing. Second, they gave us a different viewing angle. From Earth, we see 3I Atlas at one orientation relative to its coma. From Mars, during the flyby, the viewing geometry was different. This could reveal asymmetries or structures in the coma that aren't visible from our perspective. Third, they demonstrated that 3I Atlas didn't change its behavior when approaching Mars. Some of the more speculative theories about artificial origin had suggested the object might alter course to avoid planetary environments or perform close approach maneuvers near Mars. No such behavior was observed. The trajectory remained perfectly consistent with gravitational motion. But there was one set of images the public still hadn't seen, the most important ones. NASA's Mars Reconnaissance Orbiter carries the HiRISE camera, the High-Resolution Imaging Science Experiment. This instrument is capable of resolving objects on the Martian surface down to about 30 centimeters. It's the most powerful camera ever sent to another planet. Pointed at 3I Atlas, even from 29 million kilometers away, HiRISE should have captured the sharpest, clearest, most detailed images of the object yet obtained. These are the images that could potentially show surface features, reveal the true size and shape of the nucleus, and maybe, just maybe, show something unexpected. As of October 28, 2025, those images have not been publicly released. The reason, according to NASA, is procedural and frustrating. A U.S. government shutdown that began in late September has left the agency operating with minimal staff. Many scientists have been furloughed. Communications teams are offline. Data processing pipelines are running, but public releases have been delayed. This delay at this critical moment has become a vacuum, and into that vacuum speculation and conspiracy have rushed. Online forums are filled with claims that NASA has the images and they show something the public isn't supposed to see, that the shutdown is convenient cover for suppressing information, that the government knows something about 3I Atlas that would cause panic if revealed. These conspiracy theories are almost certainly nonsense.
Government shutdowns happen periodically when Congress fails to pass funding legislation. When this happens, federal agencies cease non-essential operations. Public communications are unfortunately considered non-essential. The science continues, but the press releases don't. Dr. Loeb has been publicly vocal about his frustration with the delay. "Who cares about the communication departments?" he wrote in a recent blog post. "We want to see the data from the scientists." He has a point. The high-rise images exist. They were taken. They're sitting on servers somewhere processed or being processed. Their scientific value doesn't change whether they're released today or next month, but the public interest is intense and delays feed speculation. The irony is that the images, when finally released, will almost certainly show exactly what the ESA images showed: a fuzzy comet with a visible coma, unremarkable at that resolution, giving no indication of artificial structure. But until they're released, the speculation continues. And that speculation is part of a larger story about how we communicate science, how we handle uncertainty, and how we respond when the universe presents us with something genuinely unusual. The Mars encounter gave us our closest look yet at 3I Atlas, and what we saw was consistent with a natural object. But the missing images, delayed by bureaucracy, not conspiracy, remain a piece of this story. A reminder that sometimes the most frustrating obstacles to scientific progress aren't technical limitations or theoretical puzzles, but simple human administrative failures. Meanwhile, other opportunities to study 3I Atlas are unfolding right now. Two spacecraft, neither designed for comet observation, are about to pass through its tail. Right now, at this very moment, 3I Atlas is reaching Perihelion, its closest approach to the Sun. At approximately 11:47 UTC, on October 29, 2025, the object passed just 1.36 astronomical units from our star. That's about 203 million kilometers, placing it just inside the orbit of Mars, in the region where solar radiation is intense enough to drive massive outgassing from cometary ices. For astronomers, this is the most important moment of the object's entire passage through our solar system. This is when 3I Atlas will be at its brightest, its most active. This is when the sun's heat will penetrate deepest into the nucleus, causing the maximum amount of sublimation. This is when we should be able to learn the most about its composition, structure, and behavior. But we can't see it, not from Earth anyway. The geometry of the solar system right now places 3I Atlas directly on the opposite side of the sun from our planet. From our perspective, the object is hidden behind our star. The overwhelming brightness of the sun, 400,000 times brighter than the full moon dominating the daytime sky, drowns out any possibility of direct observation. It's called solar conjunction. The object, the sun, and Earth are aligned with the sun in the middle. For about 2 weeks, from mid-October through early November, the 3I Atlas remains too close to the sun in the sky to observe with ground-based telescopes. It's like trying to see a firefly next to a searchlight. This isn't an accident of timing. It's not bad luck. It's simple orbital mechanics. 3I Atlas's trajectory brought it to perihelion at this specific date and time, and at this specific date and time we happen to be on the wrong side of the sun to watch. For most comets, this wouldn't be particularly significant. We'd lose sight of the object for a week or two, then pick it up again on the other side. We'd miss the perihelion observation, but we'd still get plenty of data before and after. But 3I Atlas isn't most comets, and the timing of this eclipse has raised questions that deserve careful examination. In orbital mechanics, there's a technique called an Oberth maneuver, named after Hermann Oberth, one of the founding fathers of rocketry and spaceflight. The principle is elegant. If you want to change your speed in space as efficiently as possible, you should fire your engines at the moment when you're moving fastest. This is usually at periapsis, the closest point to whatever body you're orbiting. The reason this works has to do with kinetic energy. When you're moving fast, any additional thrust produces a bigger change in kinetic energy than it would if you were moving slowly.
It's similar to the difference between accelerating a car that's already going 100 kilometers per hour versus accelerating from a standstill. The same amount of force has a bigger effect when you're already in motion. Spacecraft use Oberth maneuvers constantly. They dive close to a planet, fire their engines at closest approach, and slingshot away at much higher speeds than would otherwise be possible. It's how we've sent probes to the outer solar system. It's how we've achieved some of the fastest spacecraft velocities in history. Now consider the reverse scenario. Imagine an interstellar spacecraft approaching our solar system at high speed, let's say 58 kilometers per second, which happens to be 3I Atlas's velocity. If it wants to slow down to brake and enter orbit around the sun rather than just flying past, the most efficient place to do, that is at perihelion. Fire the engines when moving fastest relative to the sun, and you get maximum deceleration for minimum fuel. This would be called a reverse Oberth maneuver, and the optimal time to execute it would be exactly when 3I Atlas is reaching perihelion, today. Here's where things get interesting from a purely theoretical standpoint. If an intelligent civilization wanted to send a probe to our solar system, and if they wanted that probe to enter orbit rather than just making a flyby, the optimal strategy would be to time the arrival so that the braking burn happens at perihelion. And if they were clever, if they wanted to avoid detection during this critical maneuver, they might time it so that perihelion occurs when the probe is on the opposite side of the sun from the civilization they're approaching. In other words, exactly the geometry we're seeing right now with 3I Atlas. To be absolutely clear, there is no evidence that 3I Atlas is performing any kind of maneuver. The object's trajectory, based on thousands of observations from July through September, remains consistent with pure gravitational motion. If it were firing engines right now, we would expect to see changes in its orbital parameters when we pick it up again in November. But the geometry is nonetheless striking, and it's one of several factors that have led some researchers, most notably Dr. Avi Loeb, to suggest that we should take seriously the possibility, however remote, that 3I Atlas might be artificial. Loeb and colleagues published a paper in October 2025 exploring what they explicitly frame as a pedagogical exercise, a thought experiment designed to explore what an artificial interstellar object might look like and how we would detect it. The paper lists several characteristics of 3I Atlas that they argue are consistent with, though not proof of technological origin. The trajectory's alignment with the ecliptic plane, 89 degrees off compared to random expectation of 45 degrees average. The close approaches to Venus, Mars, and Jupiter probability, less than 0.005% for random arrival time. The perihelion eclipse from Earth's view, optimal for clandestine maneuvering. The unusual chemical composition, nickel without iron. The sunward jet potentially consistent with thrust. The extreme negative polarization, unusual optical properties. Each of these points taken individually has natural explanations. We've discussed many of them already, but the paper argues that the combination of all these factors is statistically unlikely and worthy of serious investigation. The paper's conclusion is carefully worded. It invokes Pascal's wager, the philosophical argument that suggested it's more rational to believe in God than not because the potential benefit of being right vastly outweighs the cost of being wrong.
In other words, even if the probability of artificial origin is very low, the consequences, if true, would be so significant that we should investigate thoroughly. The cost of investigation is minimal. The cost of ignoring a genuine artificial object would be enormous. It's worth noting that the vast majority of astronomers disagree with Loeb's assessment. The mainstream scientific view, represented by NASA and ESA officials, is that 3I Atlas looks like a comet, behaves like a comet, and should be treated as a comet unless and until evidence forces us to reconsider. Tom Statler, NASA's lead scientist for solar system small bodies, has stated, "It looks like a comet."
It does comet things it very, very strongly resembles in just about every way the comets that we know. Dr. Michelle Bannister, a planetary astronomer who has studied numerous comets, put it even more bluntly: there's nothing about this object that screams artificial. Everything we've seen can be explained by natural processes. These are the mainstream scientific views. They represent the consensus position, and they're based on solid evidence and reasonable interpretation of the data. But Loeb's argument raises a deeper question about how science should approach truly unusual phenomena. If an artificial interstellar probe did enter our solar system, what would it look like? How would we recognize it? What tests would we perform to distinguish it from a natural object? These are legitimate scientific questions. And they're important questions because if we ever do encounter an artificial object, we need to have thought carefully about how to identify it. The Oberth maneuver timing is just one piece of a larger puzzle. By itself, it proves nothing. Coincidences happen, but combined with everything else, the trajectory, the chemistry, the timing, it adds to a pattern that some find compelling and others find meaningless.
What we need is more data. We need to see what happens when 3I Atlas emerges from behind the Sun. We need to measure its trajectory with extreme precision and check for any deviations from gravitational motion. We need to observe its activity level and see if it matches predictions for a natural comet post-Perihelion. For now, though, we wait. The most important moment in 3I Atlas's journey through our solar system is happening right now, 203 million kilometers away. And all we can do is wait for it to reappear and see what changed during those invisible hours. To understand the debate over 3I Atlas, we need to understand the man at the center of the controversy. Dr. Abraham Avipa Loeb is the Frank B. Baird Jr. Professor of Science at Harvard University, former chair of the Astronomy Department, founding director of Harvard's Black Hole Initiative, and one of the most prolific astrophysicists of his generation. He has published over 1,000 scientific papers, advised dozens of PhD students, and received numerous awards for his contributions to theoretical astrophysics. He is also by any measure controversial. Since Oumuamua's discovery in 2017, Loeb has been the most prominent scientific voice suggesting that interstellar objects might include artificial probes from other civilizations. His 2021 book, Extraterrestrial, argued that we should seriously consider the possibility that Oumuamua was not a natural object. The book became a bestseller. It also made Loeb something of a pariah in parts of the astronomical community. Many scientists felt, and some stated publicly, that Loeb was engaging in irresponsible speculation, that he was confusing the public, feeding conspiracy theories, and damaging the credibility of astronomy by entertaining exotic hypotheses without sufficient evidence. Loeb's response has been consistent: science should follow the evidence wherever it leads, and we shouldn't dismiss hypotheses simply because they make us uncomfortable. If the data doesn't fit natural explanations cleanly, we have a responsibility to consider alternatives. With 3I Atlas, Loeb has taken this position even further. In a series of blog posts, papers, and media interviews, he has argued that this object presents what he calls a black swan event, a high-impact occurrence that is so rare it seems impossible to forecast under normal circumstances, but in hindsight appears to have been inevitable. The term comes from the historical belief that all swans were white, a belief shattered when black swans were discovered in Australia. The metaphor has been applied to financial crashes, technological breakthroughs, and paradigm shifts in scientific understanding. Events that seem impossible until they happen and then seem obvious in retrospect. Loeb's argument is this: if intelligent civilizations exist elsewhere in the galaxy, and most astronomers believe they probably do, somewhere given the sheer number of stars and planets, then at least some of them might send probes throughout the galaxy. These probes would eventually pass through other star systems. Some would pass through ours. When they do, we need to be prepared to recognize them. He has developed what he calls the Loeb scale, a ranking system for interstellar objects based on how unusual their properties are. The scale runs from 0, definitely natural, to 10, definitely technological. Most comets and asteroids in our solar system would rank 0 or 1. Oumuamua, with its unexplained acceleration, ranks about 2 or 3. Borisov, being so normal, ranks 0. 3I Atlas ranks 4, high enough to warrant serious investigation but not high enough to conclude artificial origin. The 8 anomalies Loeb lists for 3I Atlas are trajectory, aligned within 5 degrees of the ecliptic plane, 0.2% probability. Sunward jet in July-August that disappeared in September. Nucleus about 1,000,000 times more massive than Oumuamua. Unusual for detection statistics. Arrival time bringing it close to Mars, Venus, and Jupiter, while being unobservable from Earth. At perihelion, 0.005% probability. Unusual chemical composition with nickel, detected before iron. Extreme negative polarization in reflected light. Very high speed compared to previous interstellar objects. Size much larger than previous interstellar visitors, despite detection biases favoring smaller objects. Each anomaly has potential natural explanations. But Loeb argues that the combination is statistically improbable enough to warrant the hypothesis that 3I Atlas might not be entirely natural. He has compared our situation to a blind date with a serial killer, a provocative and somewhat alarming metaphor. The point he's making is that when you encounter something unknown, you shouldn't assume it's benign. You should investigate carefully, remain vigilant, and not dismiss potential dangers simply because they seem unlikely. This metaphor has not gone over well with many scientists who feel it's unnecessarily alarmist and feeds public fears that are not grounded in evidence. NASA and ESA officials have been careful to emphasize repeatedly that 3I Atlas poses no threat to Earth. It will come no closer than 270 million kilometers to our planet. There is zero risk of collision, zero risk of any kind of physical harm. But Loeb's concern isn't about collision, it's about reconnaissance. If 3I Atlas were a probe, and again this is highly speculative, it would be here to observe, not to attack. The question is, what would such a probe be looking for? What would its creators want to know about our solar system? And most unsettling, do they know we're here? Loeb has suggested that 3I Atlas might release mini-probes during its perihelion passage. Small objects, perhaps meter-scale, that could use the Oberth effect to change trajectory toward inner planets. These probes could in theory reach Earth by late December 2025, coinciding with the object's closest approach to our planet. This scenario is purely speculative. There's no evidence for it. But it's a testable hypothesis. If mini-probes exist, we should be able to detect them. We'll be watching carefully. The mainstream astronomical community has been largely critical of Loeb's approach. Some criticism is about methodology, the feeling that he's reaching conclusions not fully supported by data. Some is about communication, the concern that his public statements are being misinterpreted and amplified into conspiracy theories. But some of the criticism seems to be about something deeper: discomfort with the question itself. A sense that even asking whether an object might be artificial is somehow unscientific, undignified, or irresponsible. Loeb would argue that this discomfort is precisely the problem, that science advances by asking uncomfortable questions, by challenging consensus, by being willing to look foolish in pursuit of truth. He points out that many major discoveries in astronomy were initially dismissed as impossible or ridiculous. Continental drift, black holes, exoplanets, dark energy. The question is 3I Atlas another example of a phenomenon that seems impossible until we accept it? Or is it an example of seeing patterns where none exist, of imposing significance on coincidence? The answer will come from data, not from debate. From observation, not from opinion. And that data is coming. On November 7th, when 3I Atlas emerges from behind the sun and becomes visible again, we'll have our first chance to test the competing hypotheses.
If the trajectory has changed in ways that can't be explained by outgassing, that would be significant. If new structures or emissions appear, that would be worth investigating. If radio telescopes detect signals, that would be extraordinary. But if, as most scientists expect, the object emerges exactly as predicted, following a gravitational trajectory, showing normal post-perihelion cometary activity, with no surprises, then the natural hypothesis will be strongly supported, and the artificial hypothesis will remain an interesting but unsupported speculation. Loeb has said he's prepared for either outcome, that his goal isn't to prove 3I Atlas is artificial, but to ensure we investigate it thoroughly enough to know for certain, to make sure that if it is something extraordinary, we don't miss it through lack of attention or willingness to ask the difficult questions. That's a reasonable scientific position. The execution and communication of that position is where the controversy lies. If an artificial interstellar probe did enter our solar system, how would we know? This isn't a hypothetical question anymore. With improved telescopes coming online, particularly the Vera C. Rubin Observatory, we're going to detect many more interstellar objects, dozens per year, eventually hundreds. Most will be natural, but if even one is artificial, we need to know how to recognize it. Loeb and colleagues have proposed several criteria. Think of them as a menu of tests we could apply to any suspicious object. Shait's Atlas provides a chance to refine these tests to see what works and what doesn't to prepare for future discoveries. Test 1: radio emissions. This is perhaps the most obvious test.
Artificial objects might emit radio signals either as communication as waste heat from electronics or as active radar for navigation. CD researchers have been pointing radio telescopes at 3I Atlas for months, scanning across a wide range of frequencies looking for any unusual signals. So far, nothing. No signals detected above the background noise. No patterns that would suggest artificial origin. If 3I Atlas is a probe, it's either inactive, deliberately quiet, or communicating at wavelengths or in ways we're not monitoring. The absence of radio signals doesn't prove it's natural, but it's consistent with natural origin. Test 2: trajectory. Anomalies: natural objects move according to gravity, sometimes with small perturbations from outgassing forces. Artificial objects can maneuver. They can change course, adjust speed, orient themselves deliberately. As we've discussed, no trajectory anomalies have been detected in 3I Atlas through September 2025. The orbit follows exactly what we'd predict from gravitational motion, with perhaps tiny wobbles consistent with asymmetric outgassing. But there's a caveat. Small course corrections might be below our detection threshold, especially if they occurred early in the object's approach when we had fewer observations. The real test will come in November when we can observe the post-perihelion trajectory. If it differs significantly from predictions, that would be interesting. Very interesting. Test 3: surface features. Natural objects should look natural. Irregular shapes, rough surfaces, random patterns of light and dark caused by different materials and weathering. Artificial objects might show geometric regularity, right angles, symmetries, patterns that don't occur in nature. We don't have high enough resolution images to check this for 3I Atlas. The high-rise images from Mars when they're released might help, but even high-rise from 29 million kilometers away won't show surface details smaller than several kilometers across. We'd need a much closer flyby or a dedicated mission to see true surface features. Test 4: thermal signature. Active electronics generate heat. Even a dormant spacecraft might have residual thermal emissions from radioactive decay in its power systems, something like the plutonium-238 used in NASA's Curiosity and Perseverance rovers. These would show up in infrared observations as temperatures slightly higher than expected from solar heating alone. NASA's James Webb Space Telescope observed 3I Atlas in infrared. The thermal signature was consistent with solar heating of ice and rock. No excess detected. But again, this doesn't rule out a very efficient or very dormant artificial object. It's consistent with natural origin, but not proof of it.
Test 5. Composition. Natural objects should have compositions that make sense for their formation environment, ices that can condense at certain temperatures, minerals that form in protoplanetary disks, ratios of elements that match stellar abundances. Artificial objects might contain unusual isotopic ratios from nuclear processes, refined metals purified beyond what occurs naturally, or compounds that require industrial production. The nickel without iron observation initially seemed suspicious in this category, but as iron was later detected and as natural mechanisms for nickel carbonyl formation were identified, this anomaly became less compelling. The chemistry is unusual, yes, but explicable within natural processes. Test 6. Behavior. Natural objects follow predictable patterns. Comets brighten as they approach the sun following mathematical curves related to sublimation rates. Asteroids rotate at rates determined by their formation history and subsequent collisions. Artificial objects might show unpredictable changes, sudden brightness variations, attitude adjustments, emissions that don't correlate with solar distance. 3i Atlas has shown some unusual behaviors. The sudden water increased the direction, change of the jet, the metal emission patterns, but all can be explained by inhomogeneous composition and complex sublimation physics. Nothing requires an artificial explanation. Test 7. Structural integrity. Natural comets break apart. They fragment under thermal stress, shed material, sometimes disintegrate completely near the sun. If an object survives multiple solar passes intact or shows unusual structural stability, that might indicate artificial construction. We'll know more about 3i Atlas's structural integrity after perihelion. If it fragments, that's a strong sign of natural origin. Comets are fragile, held together weakly by gravity and frozen ices. If it emerges completely intact despite the thermal stress, that's less definitive but interesting. Test 8. Response to communication. This is the boldest test and the one most likely to seem foolish, but if you seriously consider the artificial hypothesis, it follows that you might try to communicate. Some researchers have suggested beaming radar or laser signals at 3i Atlas, deliberately structured sequences of prime numbers, mathematical constants, simple pictographs, anything to distinguish them from natural electromagnetic noise. No one has actually done this yet, as far as we know. The experiment would be expensive and unlikely to succeed, but it's theoretically possible. And if 3i Atlas responded, if it changed its trajectory, if it emitted a radio signal in reply, that would be definitive proof of intelligence. The lack of response would be less definitive. Maybe it's not artificial. Maybe it doesn't have receivers at the right frequencies. Maybe it's programmed not to respond. Maybe its creators don't want contact. None of these tests applied individually can definitively prove artificial origin. Even if SLA responded to communication, there's always the possibility of misinterpretation of natural phenomena that mimic signals of human error in detection or analysis. But a combination of positive results across multiple tests would be compelling. An object that showed trajectory anomalies and radio emissions and geometric surface features and unusual thermal signatures would be very, very difficult to explain naturally. 3i Atlas passes none of these tests, or more precisely, it shows no positive evidence on any of them. Everything observed so far is consistent with natural origin. The artificial hypothesis remains possible only because of the absence of certain data and the statistical improbability of certain combinations of features. But absence of evidence for natural origin is not the same as evidence for artificial origin. This is where the scientific method becomes crucial. The burden of proof lies with extraordinary claims. The claim that 3i Atlas is artificial is extraordinary. Therefore, it requires extraordinary evidence. That evidence hasn't materialized.
Every new observation has moved the needle further toward natural comet and away from artificial probe. That doesn't mean we should stop investigating. It means we should adjust our confidence in different hypotheses based on accumulating evidence. But the question itself was worth asking, because someday, maybe with 3I Atlas, maybe with Object 47, maybe with Object 2394, we might encounter an interstellar visitor that doesn't have natural explanations. And when that day comes, we'll need to know what to look for. The framework Loeb and others are developing isn't wasted effort, even if 3I Atlas turns out to be entirely natural. It's preparation, it's practice, it's making sure that when the truly anomalous object arrives, we're ready. There's a question we've been circling, a question that makes some scientists uncomfortable but deserves direct examination. If intelligent civilizations exist elsewhere in the galaxy, and the numbers suggest they probably do, why haven't we detected them? This is the Fermi paradox, named after physicist Enrico Fermi, who supposedly asked during a lunch conversation in 1950, "Where is everybody, Mark?" The numbers should favor contact. The Milky Way contains somewhere between 100 and 400 billion stars. Most have planetary systems. Conservative estimates suggest billions of potentially habitable worlds. The galaxy is about 13 billion years old. Stars have been forming planets for most of that time. If life and intelligence are even moderately common, if they arise naturally given the right conditions, then civilizations should have appeared millions of years before us. Some should have developed interstellar travel. Some should have colonized the galaxy. Some should have sent probes everywhere, including here. Yet we see nothing. No radio signals beyond natural sources. No megastructures visible in our telescopes. No obvious signs of large-scale engineering or galactic civilization. Just silence. The Great Silence, as it's sometimes called. Many solutions to this paradox have been proposed. Maybe intelligence is extremely rare. Perhaps we're the first in our galaxy. Maybe civilizations destroy themselves before achieving interstellar travel. Technological adolescence is a great filter that few species pass through. Maybe they're here, but hiding, or so different from us we don't recognize their presence. Maybe they communicate in ways we haven't discovered. One of the darker solutions is called the dark forest hypothesis. It comes from Liu Cixin's science fiction trilogy, but the concept is worth taking seriously from a game-theoretic perspective. The idea is this: in a galaxy where resources are finite and civilization's intentions are unknown, the safest strategy might be to remain silent, to hide, to avoid detection. Because if you announce your presence by broadcasting radio signals, by building obvious structures, by expanding visibly, you make yourself a target. Other civilizations might view you as a potential threat, as competition for limited resources, or simply as a convenient source of materials and technology. In a game theory scenario where trust is impossible and communication takes years or centuries, the rational strategy might be preemptive. Strike, destroy any detected civilization before they become powerful enough to threaten you. In this framework, the silence we observe isn't because no one is out there. It's because everyone is hiding. Everyone is listening but not transmitting. Everyone is watching but not revealing themselves. The galaxy is a dark forest where every civilization is a hunter moving quietly through the trees, ready to eliminate any other hunter they encounter. This is speculative philosophy, not science. We have no evidence that this is how the galaxy operates, but it's relevant to 3I Atlas because of what Loeb and colleagues suggest in their papers. If an advanced civilization wanted to send reconnaissance probes throughout the galaxy, operating under dark forest principles, assuming potential hostility from any civilization they encounter, what would those probes look like? They would gather information while revealing nothing. No radio signals, no obvious structures, passive observation mimicking natural objects as much as possible. They would approach, quietly study their target, and leave no trace of their visit.
An interstellar probe operating under these principles might approach at high speed to minimize detection time, come from a direction where background stars make early detection challenging, align with the ecliptic plane to facilitate close approaches to multiple planets, time its perihelion to occur when Earth's view is blocked by the sun use, that hidden moment to perform any necessary maneuvers or deploy sub-probes. Show no radio emissions or obvious technological signatures, mimic natural cometary behavior as camouflage. This describes quite closely what we're observing with 3I Atlas, which is either a remarkable coincidence or evidence worth taking seriously. But here's the problem with the dark forest hypothesis applied to 3I Atlas. It requires a chain of assumptions, each individually questionable, that becomes increasingly unlikely with each link. Requirement: one intelligent life must exist elsewhere in the galaxy. This is plausible but unproven.
The Drake equation suggests it's likely, but the great filter argument suggests it might be extraordinarily rare. Requirement 2. At least one civilization must have developed interstellar travel. This is speculative. We have no proof it's even possible to travel between stars efficiently enough to explore a galaxy. Requirement 3. That civilization must have detected our solar system as a target of interest. This requires either very advanced detection methods or blind survey of many systems sending probes everywhere. Requirement 4. They must have sent a probe that arrived precisely now during the brief window when humans are technologically capable of detecting it. 3I Atlas has been traveling for billions of years. The odds it would arrive during humanity's century of technological advancement are vanishingly small.
Requirement 5. The probe must be large enough and bright enough to be detected by our telescopes, yet show no signs of technology beyond what could be explained as natural. This seems contradictory. Requirement 6. The probe must operate under principles where passive observation is more valuable than communication or interaction. This assumes particular strategic thinking that may not be universal. Each assumption is individually questionable. Together, they form a chain that becomes exponentially unlikely. The probability isn't zero. Unlikely things do happen, but it's very, very low. Moreover, the dark forest scenario creates logical problems. If civilizations are hiding and eliminating any detected competition, how does any civilization ever become powerful enough to pose a threat? How does galactic colonization ever begin? The strategy seems self-defeating on longer time scales.
A more benign interpretation of the Great Silence is simply that space is vast. Civilizations are rare, and we're not looking in the right way or at the right time. Perhaps signals have passed through our solar system, but before we had radio telescopes. Perhaps we're being observed, but by probes so sophisticated we can't detect them. Perhaps civilizations do expand, but slowly, carefully, taking millions of years to spread across the galaxy, and none have reached our neighborhood yet. The dark forest hypothesis is intellectually interesting. It makes for great science fiction, but as a scientific explanation for 3I Atlas, it requires far more assumptions than the simple natural comet hypothesis. Still, the philosophical questions it raises are worth contemplating. If we did detect an artificial probe in our solar system, should we try to communicate with it? Should we attempt to capture it? Should we destroy it just in case? These aren't idle questions. If we're going to consider the artificial hypothesis seriously, we need to think through the implications. But we should do so carefully, without panic, without jumping to conclusions based on incomplete data. The most likely explanation for 3I Atlas remains what it's been all along: an ancient, unusual, but entirely natural comet from another star system. The dark forest scenario makes for compelling speculation, but speculation is not evidence. What we need is what we've always needed: more data. Better observations, careful analysis, the scientific method applied rigorously and without preconception, and that's exactly what's happening right now. November 7th, 2025. Mark that date. That's when 3I Atlas is expected to emerge from behind the Sun and become visible again to Earth-based telescopes. After 8 days of solar eclipse, during which the object passed through perihelion completely hidden from our view, we'll finally be able to see it again. By then, it will have changed. Perihelion is a transformative event for any comet. The intense solar radiation heats the nucleus to temperatures it may not have experienced in billions of years. Ice that has been stable for eons suddenly sublimates. Trapped gases burst out. Dust layers peel away. The object sheds mass, alters its surface, potentially fragments into pieces. For 3I Atlas, this transformation is happening right now in real time about 203 million kilometers away, and we can't watch it. When it reappears on November 7th, astronomers expect to see changes. The coma should be larger and brighter. The tail should be more prominent, possibly stretching millions of kilometers. The outgassing rate should have increased significantly during perihelion, though it will be declining by the time we see it again. But there are other changes that might be more subtle and more important. If 3I Atlas performed any kind of maneuver during perihelion, and to be clear, there's no reason to think it did, we'll see evidence in its trajectory. The orbital elements, the mathematical parameters that describe its path through space, will have shifted. Not by much perhaps, but measurably. Even a small push from engines or from asymmetric outgassing would show up as deviations from the predicted orbit. Ground-based observatories around the world are preparing for an intensive observation campaign when the object becomes visible again. The International Asteroid Warning Network has coordinated efforts to track it precisely, not because it poses any danger it doesn't, but because it represents a rare opportunity to study an interstellar object during its most active phase. The campaign will focus on several key measurements. Astrometry precise position measurements over time, allowing calculation of the exact trajectory. Any deviation from pure gravitational motion would indicate forces acting on the object, either natural outgassing or something else. Photometry, brightness measurements over time looking for variations that might indicate rotation outbursts or fragmentation. If the nucleus has split into pieces, we'd see multiple brightness peaks as the fragments separate and rotate independently. Spectroscopy, chemical composition of the coma, tracking how it changes as the object moves away from the Sun and different layers of the nucleus are exposed. This will tell us whether the unusual chemistry observed earlier persists or whether it was just surface phenomena. Polarimetry. The polarization of reflected light providing information about the size and nature of dust particles in the coma. This can reveal whether the dust properties remain consistent or change post-perihelion.
Radio observation. While 3I Atlas is too far for useful radar imaging, radio telescopes will continue monitoring for any artificial signals. The European Space Agency's Jupiter Icy Moons Explorer JUICE will observe 3I Atlas between November 2nd and 25th from a different vantage point in space. JUICE is currently on its way to Jupiter, but it's positioned to get a good view of the comet post-perihelion from an angle impossible from Earth. JUICE carries multiple instruments: Janus Visible Light Camera, MAGIS Infrared Spectrometer, SWI Submillimeter Wave Instrument, and several particle detectors. Together, these can provide a three-dimensional picture of the coma structure, the gas composition, and potentially detect molecules from the tail. The data from JUICE won't be downlinked until February 2026 due to bandwidth and communication constraints.
But when it arrives, it will provide crucial context that we can't get from Earth alone, a different viewing geometry, a different perspective on the comet's activity. In December 2025, 3I Atlas will make its closest approach to Earth, 1.8 astronomical units, approximately 270 million kilometers. This is still much farther than Mars at its closest, but it's the best viewing opportunity we'll have from ground-based telescopes. By then, the object will be cooling down, moving away from the sun. The sublimation rate will be decreasing. The coma will be shrinking, but it should still be active enough to study, and the geometry will be favorable for observation from the northern hemisphere. Amateur astronomers with decent telescopes, 8-inch apertures or larger, might be able to spot it as a faint, fuzzy patch in the constellation Virgo. It won't be spectacular. No naked eye visibility. No long, sweeping tail across the sky like Comet Neowise in 2020. Just a dim smudge moving slowly against background stars. But for those who know what they're looking at, it will be extraordinary. An interstellar visitor. A traveler from another star system. Something that has journeyed across light years and billions of years to appear in our sky for a few brief months. In March 2026 comes the final encounter. 3I Atlas will pass within 54 million kilometers of Jupiter. NASA's Juno spacecraft, which has been orbiting Jupiter since 2016, will turn its instruments toward the comet. Juno wasn't designed for comet observation any more than Mars Express was, but it carries JunoCam color camera, GIRAM infrared spectrometer, UVS ultraviolet spectrograph, and MWR microwave radiometer. These instruments can provide additional data on composition and activity, particularly in wavelengths difficult to observe from Earth due to atmospheric absorption. By March 2026, 3I Atlas will be cooling down significantly. The coma will be shrinking. The tail will be fading, but it will still be visible, still worth studying, because even as it leaves, it will be teaching us about the galaxy it came from. Every measurement we make, every spectrum we capture, every image we process, adds to our understanding of interstellar objects, of how planetary systems form, of what conditions exist around other stars, of the chemical and physical diversity of the galaxy. We've learned that interstellar comets can be wildly different from each other. Oumuamua was dry and rocky. Borisov was wet and carbon monoxide rich. 3I Atlas is carbon dioxide dominated with unusual metal emissions. This diversity tells us planetary systems throughout the galaxy don't all form the same way. Different stars, different distances, different initial chemical abundances all produce different kinds of comets. And when these comets are ejected through gravitational interactions, they carry that diversity with them into interstellar space. We live in a galaxy filled with these wanderers. Objects ejected from countless star systems over billions of years. Most drift in darkness forever, but occasionally, by pure chance, one passes through another system, and when one passes through ours, we get a glimpse of another world. Another time, another place in galactic history. That's what 3I Atlas represents, a time capsule, a cosmic postcard, a message in a bottle thrown across an ocean of stars. Even if every strange characteristic turns out to have a natural explanation, and the overwhelming evidence suggests they will, the object remains extraordinary, not because it might be artificial, but because it is genuinely alien, genuinely ancient, genuinely from somewhere else. And in 8 days, we'll see it again. We'll measure its trajectory. We'll analyze its chemistry. We'll watch its tail grow and fade. And we'll learn whether anything unexpected happened during those invisible hours behind the sun. The probability is that nothing unusual occurred, that the object followed the laws of physics exactly as expected, that it's now beginning its long, slow fade back into the darkness from which it came. But probability isn't certainty, and the gap between them, that small space where unlikely things become real, is where discoveries happen. On a clear night in 2026, somewhere in the mountains of Chile, the Vera C. Rubin Observatory will begin its legacy survey of space and time. This 10-year program will revolutionize astronomy in ways we're only beginning to understand. The telescope itself is remarkable. An 8.4-meter primary mirror, a 3.2 gigapixel camera, the largest digital camera ever built for astronomy. But what makes Rubin truly revolutionary isn't its hardware, it's what it will do with that camera. Every 3 nights it will photograph the entire visible sky, every object, every star, every galaxy visible from its location in Chile.
It will take these images, compare them to previous images, and identify anything that changed. Asteroids moving across the field, variable stars brightening or dimming, supernovae exploding in distant galaxies, and inevitably interstellar objects passing through our solar system. Current estimates suggest Rubin will detect somewhere between 1 and 10 interstellar objects per year, maybe more as the survey continues and the software improves. Within a decade, we might have a catalog of hundreds of interstellar visitors. This changes everything. With 3 objects, Oumuamua, Borisov, and 3I Atlas, we have anecdotes. Interesting case studies, but not enough to draw broad conclusions. With hundreds, we'll have statistics. We'll be able to answer fundamental questions about the galaxy. How common are interstellar objects? The answer matters for understanding how often planets eject material and how much mass is exchanged between star systems over galactic history.
What's the size distribution? Are most objects small fragments, or are large objects like 3I Atlas more common than we thought? What about composition? Are most interstellar comets water-rich like our own, or carbon dioxide-rich like 3I Atlas or something else entirely? What about trajectories? Do they tend to arrive along the galactic plane or from random directions? Are close planetary encounters rare or common? These questions can't be answered with 3 examples, but they can be answered with 300. Some of those future discoveries will be small and dark, barely detectable objects that we can track but not characterize in detail. We'll get crude brightness curves and rough trajectory data, but not much else. Still valuable, still adding to the statistical catalog. Others will be large and bright enough for detailed study. We'll point Hubble at them or the James Webb Space Telescope or whatever comes next.
We'll do spectroscopy, polarimetry, multi-wavelength observations. We'll learn their chemistry, their structure, their rotation states. A very few, might show characteristics unusual enough to warrant the kind of intensive investigation that 3I Atlas has received. Objects with unexpected trajectories or unusual chemistry or behaviors that don't fit standard models. And maybe someday one of them will show characteristics that genuinely can't be explained naturally, that resist every attempt at conventional interpretation, that force us to seriously consider the hypothesis we've been discussing as speculation. This is the real value of the framework Loeb and others are developing. Not because we expect to find artificial objects most scientists don't, but because we need to be prepared if we do. The search for extraterrestrial intelligence has traditionally focused on radio signals. SETI, the search for extraterrestrial intelligence, has been scanning the sky for decades, looking for deliberate transmissions from other civilizations. But interstellar objects offer another approach, sometimes called artifact SETI, looking for physical evidence rather than radio signals. And it has some advantages. Radio signals decay with distance. They spread out, become diluted by the inverse square law, eventually become indistinguishable from background noise. A powerful transmitter might only be detectable out to a few hundred light years, maybe 1,000 with our best receivers. But a physical object traveling through interstellar space doesn't decay. It just keeps moving. A probe launched 1 million years ago is still out there somewhere, traveling at whatever speed it was given. If it happens to pass through our system, we can see it regardless of how long ago it was launched. The probability of any given probe passing through our specific system is vanishingly small, of course. But if technological civilizations are common, if they send out many probes, if those probes travel for millions of years, then the total number of artificial objects in the galaxy might be substantial. Some calculations suggest that if just 1% of stars host civilizations that send out probes, and if each civilization sends out 1 million probes over its lifetime, there could be billions of artificial objects wandering the galaxy.
With billions of artificial objects among trillions of natural ones, the ratio is still very low. But it's not zero. And with improved detection capabilities, we might actually be able to spot them if we know what to look for. 3i Atlas has helped us refine those criteria. We now know that trajectory alone isn't enough. Unusual alignments can happen naturally. Chemistry alone isn't enough. Exotic compositions can form in exotic environments.
Size alone isn't enough. Large interstellar objects are rare, but not impossible. What we need is a combination of multiple factors that collectively can't be explained by any natural process. And even then, we need to be cautious. The history of astronomy is full of phenomena that seemed artificial until we understood them better. Pulsars, when first discovered in 1967, were briefly thought to be alien beacons. The regularity of their signals was so precise, so artificial seeming, that the discoverers half-seriously called them LGM signals, little green men. They're actually rapidly rotating neutron stars. Quasars were mysterious for decades. Their enormous energy output from tiny regions seemed possibly artificial. They're now understood as supermassive black holes. Fast radio bursts were puzzling when first detected in 2007. Single intense pulses of radio emission from random directions. Some suggested alien signals.
They're now understood as natural astrophysical phenomena, though the exact mechanism is still being worked out. The universe is full of things that seem impossible until we figure out the physics. Natural phenomena can be stranger than anything we imagine. This is both humbling and exciting. Humbling because it reminds us how much we don't know. Exciting because it means there are always new discoveries waiting. So when we encounter something unusual like 3i Atlas, the right approach is careful investigation, not immediate conclusion. Measure everything we can. Consider all hypotheses. Gather more data until one explanation becomes overwhelmingly more probable than the others. That's what science does. That's what distinguishes scientific thinking from speculation. And that process works. It's worked for 3i Atlas. Despite all the unusual characteristics, despite the speculation, the scientific consensus has moved steadily toward natural comet. The same process will work for future interstellar objects. Most will be boring, small, faint, unremarkable, except for their origin. Some will be interesting, unusual compositions, weird, activity patterns, unexpected properties. A few might be genuinely puzzling, requiring new physics or chemistry to explain. And maybe, just maybe, one will be artificial. If that day comes, if we detect an interstellar object that shows clear evidence of technology, it will be the most important discovery in human history. But until that day, we should approach each discovery with scientific rigor. Curiosity? Yes. Openness to possibilities, absolutely, but also skepticism, careful analysis, and recognition that extraordinary claims require extraordinary evidence. 3i Atlas has been extraordinary enough. It's taught us about interstellar diversity, about ancient comets, about exotic chemistry. That's more than enough. We don't need it to be alien to be significant. The age of interstellar astronomy has begun. We're learning to read messages written in ice and stone and chemistry, messages that traveled across light years to reach us. 3i Atlas is one message, and there will be many more. Set aside the speculation for a moment. Set aside the artificial hypothesis, the dark forest theories, the dramatic possibilities. Strip away all the debate and focus on what we know, what we can measure, what we can learn from 3i Atlas, regardless of what it ultimately is. This object is old, very old, based on its trajectory and velocity traced backward through time, accounting for the gravitational effects of nearby stars over billions of years. 3i Atlas may have been ejected from its home system somewhere between 7 and 10 billion years ago. Think about that time span. Our Sun is 4.6 billion years old. Earth is the same age. The oldest rocks on our planet are about 4 billion years old. The oldest fossils are 3.5 billion years old. All of human civilization, all of recorded history, spans less than 10,000 years. 3i Atlas has been traveling through the galaxy for twice as long as our planet has existed. It formed when the universe was younger, when the Milky Way had different chemical abundances, when stars were forming at different rates in different regions. The chemistry of this object is a window into that ancient time. Every molecule we detect, every isotope ratio we measure, every grain of dust in its coma is a data point about conditions in the early galaxy. The dominance of carbon dioxide over water tells us about temperature and pressure in its birth protoplanetary disk, the presence of organic compounds. Cyanogen-carbon chains tells us about the raw materials available for building planets and potentially life. The metal content nickel-iron and other trace elements tells us about the supernova that enriched that region of space before the object's home system formed. Different types of supernova produce different elemental ratios. By measuring what's in 3i Atlas, we're learning about stellar evolution and death billions of years ago. This is forensic astronomy, using the evidence we can measure now to reconstruct events that occurred in places we can never visit, at times we can barely imagine. And it's not just about the past. It's about understanding the present diversity of the galaxy. Every interstellar object we study teaches us that planetary systems vary enormously, that there's no single normal way for a solar system to form and evolve. Our own system has 8 planets, dozens of moons, countless asteroids and comets, all with their own characteristics. But that's one data point, one example. We've discovered thousands of exoplanets around other stars, and they show remarkable diversity. Hot Jupiters orbiting closer to their stars than Mercury is to our sun super-Earths, with no analog in our system planets on wildly eccentric orbits. Interstellar objects add another dimension to this picture. They show us what the small bodies, the asteroids and comets, are like in other systems. And since these small bodies contain the leftover building blocks from planet formation, they tell us about the raw materials and conditions that created those distant worlds. 3i Atlas's carbon dioxide dominance suggests it came from a system where volatile ices condensed in abundance at larger distances from the star. Maybe its parent star was cooler than our Sun and M-dwarf, where the habitable zone is much closer in. Or maybe it formed in an unusually cold region of a protoplanetary disk, far from its star's warmth. The water we've detected, even though it's less abundant than CO2, tells us that water is widespread in the galaxy. This is crucial for astrobiology. Life as we know it requires water. If interstellar comets commonly contain water, that means the building blocks for life are being distributed throughout the galaxy, seeding new star systems with the ingredients needed for biology. The organic compounds are equally significant. Complex carbon-based molecules forming naturally in cometary ices suggests that the chemistry leading to life might be universal, or at least very common. The same processes that created the organic compounds on Earth billions of years ago are happening around other stars. 3i Atlas has been exposed to the interstellar medium for billions of years. Cosmic rays, high-energy particles accelerating through space, have been bombarding its surface, breaking chemical bonds, creating radiation damage. This long exposure likely altered its structure, creating a fractured, weakened interior quite different from the pristine comets preserved in our own Kuiper belt. This could explain some of its unusual behavior, the sudden outbursts, the layered composition, the changes in metal emissions. After billions of years in deep space, the object may be fundamentally different from younger comets, even if they started with similar compositions. These are messages written in ice. Chemical signatures of another time, another place. Every measurement adds a piece to a puzzle that spans the entire galaxy, and the remarkable thing is we're just beginning to read these messages. 3i Atlas is the third sentence in what will become a long book. Within a decade, we'll have hundreds of these visitors cataloged. Each one will tell a different story. some from young systems just forming, some from dying systems where planets are being torn apart by expanding red giants,
some from the galactic core where stars are densely packed, some from the sparse outer regions where star formation has nearly ceased. Together, they'll paint a picture of the galaxy far more detailed than any telescope alone could provide.
Because while we can see distant stars and measure their properties, we can't directly sample their planetary systems. We can't touch the comets orbiting them, can't analyze their chemistry directly. But when those comets are ejected and come to us, we can do exactly that. We can touch metaphorically through spectroscopy worlds light years away. We can hold in our data a piece of another star's story. This is why 3i Atlas matters, regardless of what it is. This is why it's worth the telescope time, the scientific effort, the public attention. Not because it might be alien technology, it almost certainly isn't, but because it's genuinely extraordinary in what it can teach us about our cosmic neighborhood. We are not isolated. Our solar system is not unique. The galaxy is full of variety, full of chemistry, full of processes we're only beginning to understand. And occasionally, that galaxy sends us a gift, a sample, a visitor that carries within it secrets we couldn't learn any other way. 3i Atlas is one such gift, and we should be grateful for it. Let's end where we began, with what we actually know, with facts instead of speculation, with observation instead of interpretation. 3i Atlas is an interstellar object. This is confirmed by its hyperbolic trajectory and high velocity relative to the Sun. It did not originate in our solar system. It came from somewhere else, and it's leaving for somewhere else. It was discovered on July 1, 2025 by the Atlas Telescope Network in Chile. The discovery itself is a testament to improving detection capabilities. 20 years ago, we likely would have missed this object entirely. It measures approximately 5 to 6 kilometers in diameter, possibly larger.
This makes it the largest interstellar object, yet detected roughly 1,000 times more massive than Oumuamua. It is composed primarily of carbon dioxide ice with water ice and various other volatiles in smaller quantities. This composition is unusual compared to solar system comets, but explainable by formation in a different stellar environment. It has been observed to emit nickel vapor initially without detectable iron, though iron emissions appeared later. The mechanism behind this unusual metal emission pattern is still being studied with natural explanations involving exotic chemistry in the coma. It displayed a sunward-pointing jet in July and August 2025, which transformed into a conventional anti-solar tail by September. This behavior is consistent with rotating nucleus with sun-facing active regions observed in other comets. It passed within 29 million kilometers of Mars on October 3, 2025, allowing spacecraft around Mars to capture the closest images yet obtained of an interstellar object. These images showed a comet-like appearance with a visible coma. It reaches perihelion today, October 29, 2025, at approximately 1.36 AU from the Sun. This perihelion passage occurs while the object is hidden from Earth's view by solar glare. It poses no threat to Earth. Its closest approach to our planet will be approximately 1.8 AU 270 million kilometers in December 2025. There is zero risk of collision. Its trajectory is consistent with pure gravitational motion. Thousands of position measurements from July through September show no confirmed evidence of non-gravitational acceleration beyond what might be expected from asymmetric outgassing. The nickel-to-iron ratio anomaly observed in September remains partially unexplained. While iron was later detected and natural mechanisms have been proposed, the initial absence of iron in detectable amounts is unusual and warrants further study. The extreme negative polarization in reflected light is unprecedented among known comets. This suggests unusual dust properties, particle size composition, or structure that we don't yet fully understand. The statistical improbability of the trajectory. While low probability doesn't mean impossible,
The combination of ecliptic alignment and close planetary encounters is genuinely unusual. Whether this represents chance or something more cannot be definitively determined from one object. The true internal structure remains unknown. Is it a solid nucleus? A rubble pile held together by gravity? A layered structure with different compositions at different depths? We won't know until we get better images or detect fragmentation, the exact formation environment and age. While we can infer it's ancient and from a cold region, we cannot identify which star system it came from or when precisely it was ejected. The overwhelming evidence supports natural origin. Every major observation has a plausible natural explanation. The chemistry, while exotic, involves compounds that can form in cometary environments. The trajectory, while unusual, is possible through pure gravitational dynamics. The behavior patterns match complicated but natural sublimation physics. No technological signatures have been detected. No radio signals, no obvious structures in the available images, no trajectory deviations indicating active control. The object looks like a comet and behaves like a comet. The artificial hypothesis remains possible in the sense that we cannot prove a negative. We cannot prove with absolute certainty that 3I Atlas is natural. But the burden of proof lies with extraordinary claims, and the evidence for artificial origin is insufficient. This doesn't mean the question shouldn't have been asked. In science, asking uncomfortable questions is how we make progress. Testing unlikely hypotheses is how we ensure we're not missing something important. But asking the question and concluding the answer are different things. The question, could this be artificial, is legitimate. The answer based on current evidence is almost certainly not. In 8 days, 3I Atlas will emerge from behind the sun. The first observations will focus on trajectory, measuring its position precisely, checking for any deviations from predicted orbit. If the path has changed in ways unexplainable by outgassing, that would warrant immediate investigation. The second priority will be activity level. Has the coma expanded as expected? Is the tail more prominent? Are there signs of fragmentation or unusual outbursts? These observations will tell us how the perihelion passage affected the object. Spectroscopic observations will continue through December, tracking chemical changes as different layers of the nucleus are exposed. This data will be compared to models of cometary evolution to see if 3I Atlas follows expected patterns. The December 19th Earth closest approach provides our best opportunity for detailed ground-based observation. Professional and amateur astronomers will be watching, gathering data, contributing to the global understanding of this visitor. The March 2026 Jupiter encounter offers one final chance for spacecraft observation before 3I Atlas becomes too faint to study. After that, it fades into the darkness, another data point in the growing catalog of interstellar objects. But here's what keeps astronomers awake at night. Not conspiracy theories, not alien probes, but genuine scientific mysteries. Why do interstellar objects show such extreme diversity? 3 visitors. 3 completely different profiles. What does this tell us about planetary system formation throughout the galaxy? How common are these objects? Really? Are we seeing a representative sample, or are detection biases giving us a skewed picture? What happens to them over billions of years in interstellar space? How does cosmic ray damage, micrometeorite bombardment, and temperature cycling change their structure and composition? And the biggest question, when will we detect one that truly doesn't fit our models? One that forces us to expand our understanding of natural processes or to seriously consider that we're not alone. These are the questions worth asking. These are the mysteries worth pursuing. Not because we expect dramatic revelations, but because this is how science works. One observation at a time. One object at a time. Building understanding incrementally, carefully, without jumping to conclusions. 3I Atlas has given us an incredible gift.
Not proof of alien visitation, there is no such proof, but something perhaps more valuable, a reminder of how much we have yet to learn about the universe. A reminder that the cosmos is stranger, more diverse, and more wonderful than we imagined. And that reminder comes with a promise there will be more visitors, more mysteries, more opportunities to look up at the sky and wonder what stories those distant points of light might tell us if only we learn to read them. Right now, 203 million kilometers away, hidden behind the overwhelming brightness of our sun, something is happening. 3I Atlas is experiencing heat. It hasn't felt in billions of years. Ice is sublimating. Gas is streaming into space. The ancient structure forged in another star system, preserved in the cold of interstellar space, is being transformed by our sun's radiation. We cannot see it. We can only wait. In 8 days, we'll know what survived. We'll measure, we'll analyze, we'll compare to predictions. And the overwhelming probability is that we'll see exactly what we expect: a comet changed by perihelion in ways we understand, following a trajectory determined purely by gravity. But probability is not certainty. And in that gap, that small space between what we expect and what we observe, lies the possibility of surprise, the possibility of discovery, the possibility that the universe still has secrets we haven't imagined. This is why we watch. This is why we measure. This is why we ask questions that might seem impossible. Because occasionally the impossible becomes real. Because sometimes the universe surprises us in ways that change everything we thought we knew. 3I Atlas will almost certainly turn out to be a natural object. An unusual object, yes. An ancient traveler carrying messages from another time and place. But natural. Explainable, within the boundaries of known physics and chemistry. And that's wonderful. That's enough. Because even as a natural object, 3I Atlas teaches us that the galaxy is full of variety, that planetary systems evolve in countless ways, that the raw materials for planets and possibly life are scattered throughout interstellar space, creating connections between star systems that would otherwise be isolated. We are part of a larger story. Our solar system is not alone, not unique, not separate from the rest of the galaxy. We are one system among billions, and occasionally we receive visitors from those other systems, cosmic ambassadors, whether they know it or not. Each visitor teaches us something new. Oumuamua taught us that interstellar objects can be strange and challenging to explain. Borisov taught us that they can also be reassuringly normal. 3I Atlas is teaching us that diversity is the rule, not the exception. And in a few years, the Vera Rubin Observatory will begin detecting these visitors regularly. 1 per month, then more. Within a decade, we'll have transformed interstellar objects from rare curiosities into a population we can study statistically. We'll answer questions we can't even ask right now because we lack the data. That future is coming. That era of discovery is nearly here. 3I Atlas is a preview, a taste of what's to come, so let's appreciate it for what it is. Not an alien probe, almost certainly not. Not a threat, definitely not. But a genuine marvel. A visitor from the cosmic ocean. A message in a bottle that traveled farther and longer than any human artifact ever will, arriving at our shores by chance, giving us a brief opportunity to read what's written inside before it continues on its eternal journey. Tonight, somewhere in the universe, another interstellar object is beginning its own journey. Ejected from a distant planetary system by gravitational interactions we'll never witness. Starting a voyage that will last billions of years, crossing light years of empty space, perhaps eventually passing through a solar system where beings we cannot imagine will point their instruments at the sky and wonder what this ancient visitor might tell them. That's the story 3I Atlas represents. Not invasion, not reconnaissance, just the natural consequence of a galaxy in motion, where gravity throws objects between stars, where chemistry creates diversity, where physics connects worlds that will never touch.
and we improbably, wonderfully, are here to witness it, to measure it, to learn from it, to be reminded that we are part of something larger than ourselves. The universe is not silent. It speaks, in the whisper of cosmic radiation, in the glow of distant starlight, in the chemistry of ancient ice. Three-Eye Atlas is one word in that cosmic language, and we are learning slowly to read.
The final question. If Three-Eye Atlas is just a comet, remarkable, ancient, exotic, but natural, then what will the truly anomalous object look like when it finally arrives? What will be the signs that cannot be explained away? What evidence will be so compelling that even the skeptics must pause and reconsider? And more importantly, when that moment comes, will we be ready to recognize it? Or will we be so focused on finding conventional explanations that we miss the extraordinary truth hiding in plain sight? The universe waits, patient, mysterious, full of wonders we have yet to discover. And somewhere in the darkness between stars, the next visitor is already on its way. This documentary presents the scientific understanding of Three-Eye Atlas as of October 29, 2025. The object remains under active study. Interpretations regarding artificial origin represent minority scientific viewpoints and should be understood as speculative rather than consensus positions.
The overwhelming scientific evidence supports a natural cometary origin. All scientific claims have been sourced from published research, official space agency statements, and verified astronomical observations. Speculative hypotheses have been clearly labeled throughout. For those following, the continued observation of Three-Eye Atlas updated data is available through the Minor Planet Center, NASA's JPL Horizons system, and official ESA and NASA communications channels. The cosmos reveals its secrets slowly to those willing to watch and wait and wonder.